So a piston cylinder device whose piston is resting on top of a set of stops initially contains 0.5 kg of helium gas at 100 kPa pressure and 25 degrees centigrade temperature. So if you see the figure here, guys, this is the piston cylinder device. We have the piston here, this is our cylinder, and initially, we know the it is filled with helium, and the pressure is 100 kPa, temperature is 25 degrees centigrade temperature. So the mass of the piston is such that 100 kPa of pressure is required to raise it. So if we actually want to raise this piston, we actually need 500 kPa of pressure. Question is, how much heat must be transferred to the helium before the piston starts rising? So the Q is actually the heat, the energy we are just transferring into this cylinder. So how much energy actually we need, how much heat we need, that we actually need to calculate. So if you start with this problem, what we will do is we'll write down the assumptions at first. So let's write down the assumptions. This is very important. So in this case, definitely our assumption is the first assumption, it will be helium gas. It is helium, definitely this is an ideal gas. So our assumption is helium is an ideal gas with constant specific heats. So our assumption is specific heats, it is not changing. So we can say helium is an ideal gas with constant specific heat. Okay, with constant specific heat. So that's our first assumptions, and the second assumption is this it is a system here, it is a closed system. So what we can say, guys, we can say the internal the kinetic and the potential energy changes are negligible. Again, we consider, we assume that the change of the kinetic energy and the potential energy, okay, it is close to, it is negligible. We're not telling this is zero, but we said, okay, it is close to zero. It is not a rigid, it's not explicitly mentioned here, but as it is a closed system, we said the change of this potential and the kinetic energy, it is negligible, it is very close to zero, but it is, we didn't say it is equal to zero. And also the thermal energy is stored into this in this cylinder itself is negligible, so we're not writing that on, and no other work interaction involved in this case. So that's actually all of our assumptions. Now if we write down the properties based on our assumption, we said it has constant specific heat, the helium. So 25 degrees centigrade temperature, so say this is the room, we can say the specific heat of the helium at room temperature CV, we can say 3.1156, it is kilojoule per kg Kelvin, and you will get this table from this provided from table A2. It is from A2 of your appendix. So this is actually the the properties of helium. So now if we start with the analysis, let me write down. So what we did so far, we just write down the assumptions and the properties. So we actually need the if we read the question here, look, we need how much heat we need to transfer into the helium. So we need to calculate the Q in, that we need to calculate. So what we can write from the energy balance equations here, what I said earlier, it is a closed system. So we say the helium is inside this cylinder, and as it is a closed system, so no mass can transfer, right? No mass can transfer. So the energy balance for this constant volume closed system, this is a constant volume closed system. When it is a constant volume closed system, that means we can write the energy balance equation is like this. Let's say the energy in this is actually the the formula delta E, the system. So it can be this energy in, energy out. It is actually the net energy transfer by heat, work, or mass, whatever it is. So here actually the energy in is, you can see this Q. So we can say this is Q in. What is our energy out? So we do not have any energy going out of the system. So this is only, we have the energy in. It will be equal to the the internal energy here. So we have the energy here inside the cylinder. So that's actually the internal energy. So the energy we are just applying here, it is actually the internal energy, the rate of change of the internal energy. And when we know, actually, in this problem, if you read again, we know the mass. So initially it contains 0.5 kg of the helium gas. So when we know the mass, then we can write it down like this. Q in, it is equal the mass, and the delta, we know the formula actually, delta U, it is mass, and U2 minus U1. The final internal energy minus the initial internal energy, U2 minus U1. But here, if you see clearly, we do not know the initial internal energy and the final internal energy. But what do we know, guys? We know the temperature. We know the temperature, and our assumption was, if you can see previously, our assumption was, look here, it is an ideal gas with constant specific heat. So we know the CV. So we can easily write down this expression in different ways. Actually, here this U2, the internal energy, we know the definition, we know the formula for internal energy. So let me write it down here. We know for internal energy, U equal, we can say it is CVT. Okay, CVT, that we know from the formula. So definitely I will discuss this during the lecture. So if it is E1, then we can say it is CVT1. If it is EU2, then we can say it is CVT2, right? So if we say this is equation 1 or A, then from equation A, what we can write? The Q in, it is equal, M, it is CVT2 and CVT1. Because we know mass, we know CV constant, and we know T1. So T2 actually we don't know. So now what we can do, guys, we can CV is the common term here, so we can make this term common. So what we can write from this, we can write it like this. So Q in, it is equal M CV T2 minus T1. Let's say this is equation B. So we need to calculate this. So we know mass, we know CV, we know T1. Only thing we don't know, it is T2. So now we can use the ideal gas relation to calculate this final temperature. So from ideal gas relation, what we know, guys, we know P1 V1 T1, right, this way. So here it is we said it is a constant volume problem, so we can say P1 and P2 is same. So in that way we are writing it is P1 V. So P1 V T1, it is equal P2 V T2. I'm telling again, we can write it as V1 V2, but here it is a constant volume problem. So what we can do, we can just eliminate this term V, and then it will be P1 T1 P2 T2. So that means T2, it will be P2 T1 P1. substitute the value. P2 is 500 kPa, T on I think 25 plus 273. So this is Kelvin, and P1 is 100 kPa. So kPa eliminate this two, so 5. So it will be actually 1490 Kelvin. So we got this is actually T2. So once we know T2, guys, then we can substitute the value here. So now what we can do, from equation B, we can say Q in, it is equal mass. So mass equal 0.5 kg into CV 3.1156, and it is kilojoule per kg Kelvin. And T2 is, we got 1490, and T1 is 298 Kelvin. So it will be 1857 kilojoule. So the Q in, it is 1857. So that's actually the solution of this problem. That's the energy we transferred to raise the this piston. So that was the problem. The question, if you can remember, when I read the question, the cylinder, it was equipped with a set of stops for the piston to raise on its initially filled with this helium gas at 100 kPa and 25 degrees centigrade temperature. So we need to calculate the amount of heat actually we need to raise this piston at this pressure. So what we did, if I do a quick review, I write down the assumption. I said it is a constant specific heat. Helium is ideal gas with constant specific heat. Delta K, delta P is negligible. We didn't say it is 0, but we said it is negligible. So CV from the appendix table A2, we got this, and now we know from the energy balance equation here. So we are applying only this energy in, it is equal to this internal energy. So we what we did, we just write down delta U, it is equal mu. So here mu to u1, the difference, but from the internal energy relation we know U equals CVT, then we can write U1 equals CVT and U2 equals CVT2, and then I believe it is very simple calculation. And finally the T2 was unknown, so we used the ideal gas relation. So I believe you understand this. If you have any confusion, then maybe we can discuss during the lecture. So that's it.